Okay, it's recording. Okay, so welcome to a new unit. This is called a continuous probability distributions. It's going to focus on something called the normal distribution, which is very common. It's a very common distribution that is, most of the distributions we see in real life are normal distributions, so we'll focus in on that. So let's do a little bit of a recall first. Recall the definition of continuous data, provided you a few examples. Can somebody tell me, can you unmute and tell me what continuous data is? Anybody? So continuous data can have, this was part of your test that we just had, so how do I finish the sentence? Oh, you're all shy today. Okay, continuous data can have infinite number of possible values. So what's the opposite of continuous? If it's not continuous, it's
discontinuous.
Yeah, I guess that's a good word, but another word also begins with a D.
Discrete.
Discrete. There you go. Awesome. So examples of continuous data are if you measured everyone in Canada and recorded their height and their weight, you would have a continuous distribution. Or if you recorded your wait time for a bus, you could be waiting a few minutes. You can wait a minute and 57 seconds, a minute and 58 seconds, 2 minutes and 1 second, and you can even go further and be more precise to the thousandths of a second and all that. So waiting time for next bus would be another one, and there's lots of examples. All right, so in the past, like when you were in grade 7, and if you wanted to make a chart, if you measured everyone in Canada and measured their height, and you can make a chart. What would the chart look like? What would you call the chart? And the chart would look something like this. Maybe you have, let's say, you have age down here, and you have the 0 to 20-year-olds. I'll zoom that in a little bit. I'm writing a bit small. And then maybe you have the 20 to 40. Maybe you have more people in age 20 to 40, and then people like myself. What are we called? People like myself between 40 and 60. Our generation. Does anybody know what we're called? People that were born after the World War II.
Oh, a boomer.
We are boomers. All right, so yeah, there's a lot of us, and then from 60 to 80, maybe there's quite a bit less, and then maybe from 80 to 100, people start dying off, and then 120. I don't think there's anybody past 120. So, and we could just measure the absolute frequency, and this could be like millions of people, right? You could be like, I don't know, how many people, what's the population in Canada? 35 million, something like that, 35, 30, something like that, 36 million. So maybe 8 million are between 0 and 20, maybe 10 million are between 20 and 40, and so on, right? So frequency would be just the numbers. Or if you took numbers and divided by the total population, you could convert that to probability or something, right? What's the probability if you selected a random person that they would be in there? So you could either record it as frequency or probability, right? Either one. Frequency would be in millions. Probability would be as a number between 0 and 1. Right? And so that's an example. What do we call this type of chart?
A bar graph.
Bar graph.
Not technically, it's not a bar graph. A bar graph is more like this, where you have like this is a bar graph. Bar graph would be who is your favorite Teletubby, and something like that, and you would have, what are their names? Poe. Does anybody know the Teletubbies at all? Dipsy. I think Dipsy was one. Favorite Teletubby. You guys have no idea what I'm talking about, do you?
So I know Teletubbies.
The Teletubbies are a show for preschoolers, right? And
Yeah.
they had, I forget the other one's names. Lala, I think Lala was one. I can't remember the last one. And so, how is this data different from that data? This is a bar graph. So, what do you notice between this one and this one?
That they're not connected.
Yeah, so this is continuous data, numerical data. This is not, they're not connected. So this is typically a situation where there's a bar graph. It could be numerical data still, but they're not connected. Does that make sense? Whereas this is a different name. Begins with an H. I know you know the name.
So is it histogram?
Histogram.
Oh, where'd you learn this word from?
Guys, I have to apologize. Typically, we would have done the single variable and the two variable data chapters by now. We haven't, so I'm going to continue on with probability distributions, but to make sense of this unit, it makes sense to have a little bit of review of what the mean is, what the mode is, what standard deviation is. So I'll do some of that as well, just a little bit of an upgrade on that. All right, so you can make these bins. We call these bins, or bars or whatever. You can make them smaller and smaller and smaller and smaller, right? You can make, instead of 0 to 20 years, you can do 0 to 1 and 1 to 2, and do it by year. Or you can even do it by month within a year, or even by weeks within a month, right? So you could make it really, you could call it something else. You could do the same graph, but start at 0 and 120, age in years. But you could make it a smooth curve. You could make it look something like this. Basically, does that make sense? You can imagine having very, very thin bins, so thin that you can't even see the bins anymore. Like so, just looking at the trend. We can't call it probability. We call it probability density. Okay, so. Right, so if you make the bins really, really small to the point where they're one exact little point, then you have a probability density curve. All right, so let's just continue on. However, as sample size increases, the tops of the bins tend to look smooth and take the appearance of a curve. Continuous probability distributions involve continuous variables and are usually graphed as smooth curves. The curve itself represents the probability density. If you draw it as a smooth curve, it turns into probability density, the probability per unit of the continuous variable. That makes sense? So we're just taking a chart, histogram, and making the bins infinite in number, so that the bins actually just disappear, and all you see is the top values. All right. So often you want to find a probability that a variable falls in a particular range of values. This kind of probability can be determined from the blank under the distribution curve. So let's say I wanted to find area. Awesome. Thanks for joining in. Okay, and if you convert it to a probability curve, not as a frequency curve, but if you do it as a probability, what's the area of all these things added together?
The sum of the probability,
which has to equal 1. So the area underneath this, or the area underneath this, has to equal 1. All right. So we're looking at a couple of different types of distributions. The first one is a uniform distribution, and it's not that common, but we'll talk about it. So uniform distribution, when data is uniformly distributed, the probabilities of all outcomes are, what does uniform mean?
Oh, it's either yes or no. Like it's only 2 outcomes.
Oh, no, it's
discrete and continuous.
No. When something is uniform, if you guys dress in a uniform, you all look the same. Yes. All right. All right. So, for example, the driving distance of Tiger Woods' drives off the tee is found to range evenly between 300 and 340 meters. Sketch the probability density curve. Now, I'm going to say right off the bat, is this realistic? If Tiger Woods hits a drive, is it going to be an equal chance that he's going to get a 300-meter length or a 340-meter length or something in between? well, would you expect that? Like, this is a short distance for him. This is a long distance. Would you think that this is realistic?
No, it's not.
Why not? I'm going to say you're right. It's not realistic, but we're going to use it for a demonstration anyway. So, in reality, wouldn't it be more clustered towards like the middle, like the 320? Like there'd be more at 320 than at either end? Wouldn't you think so? Anyway, I would think so. You know, so I'm going to say not realistic. The curve would be bell curved. It would be bell shaped in reality. All right, but we're gonna presume this is true. Okay, so sketch the probability density curve. So probability density is going to be prob density. Okay, you're going to have a number between 0 and 1. Then you're going to have length, drive length. And this is in what, yards? What is it? Yeah, meters. All right. So the curve, well, let's say it's 0. We'll do a little, you know, one of those little breaks where you kind of, everyone know what that means?
I know, it's like, so you can like skip like a whole bunch of numbers.
Yeah, we'll
so
skip.
You can go straight to like 20.
Yeah,
and then like go up by 5s.
Yeah, we'll skip all the way to 300. How's that? Or close to 300. Let's say 300 is here. And then, and then we'll put 340 over here. All right, so I skipped a lot between 0 and 300, but it doesn't matter because, okay, so the probability is, it's a uniform distribution, so they're all equal. So the probability will be equal between there. That's what uniform means. And he gets nothing, he never hits a tee shot under 300, and he never hits a tee shot over 340, so it just kind of drops like that. Right? Again, it's not realistic, but let's assume it is. So the question is, what the heck is that number? What number is that? What is this?
It's 1.
Is it? So remember, what did we say about the area? The area underneath the curve has to equal
1.
So what is the area under the curve?
I'm going to certainly do the math for you. Just hold on. Wait, 40? Wait, hold on.
What is the area of a rectangle?
Length times width. Oh, it's 40.
So what's the length? So this distance here is 40 meters, right? So length.
1 over 4.
So 1 equals 40 times the width.
1 over 40.
Yeah, so the width equals 1 over 40, which is, as a decimal is, width equals 0.025. So that's what this is, 0.025, or 1 over. You could. Oh, sorry. All right, that makes sense. So on a uniform probability distribution, they all have the same length, same probabilities, and it's pretty easy to determine what the probability density is. You just have to do the area of a rectangle. Okay, let's look at B. What is the probability that his next drive is greater than 330? So 330 would be like right there. All right, so what is that probability?
It wouldn't be 1 over 30? Oh wait, never mind.
The probability of the drive being greater or equal to 330 equals, now we're talking about what's the area of that? Right? So, right? We're going to ignore this part because we don't care about under 330. We just care about this part. What's the area of this?
10. Or, oh wait, sorry.
10 is this? Yeah, 10 is 330 to 340 is 10 meters, right? right? That's
so it would be 1/4 the area.
And then, what's the width again? What's the width?
0.02.
0.025. So the probability is going to be 0.25, which equals 25%, which makes sense, right? If you chop this into 4 pieces, it'd be, 25% of the times is going to be between 300 and 310. 25% of the times is going to be between 310 and 320. 25 between 320 and 330, and lastly 25% between 330 and 340. That makes sense. All right. It's not that common, so let's look at something that's more common. Okay? We're good? Flip the page? Yes, no? I guess that's a yes. All right.
Yeah.
What is the probability that his next drive is exactly 330 meters? So exactly 330, like right there. What's the area underneath 330?
0.025.
Yeah,
Is it 0?
it's 0. Which is why did you say 0?
Because if you were to do length times width, if you're at 330, then there's no length.
There's no length, right? It's just your rectangle isn't a rectangle; it's a straight line, and the area of a straight line is 0, right? Does that make sense? So with continuous data, the probability of any specific outcome is 0. It's a paradox. Okay, let's write that down. So for discrete data, an event with probability of 0 is, what's the word? For the stuff that we've done so far with discrete data, if you get a probability of 0, it is impossible. Right? An example would be rolling 3.5 with dice. You can only get 3 or 4. It's impossible to get 3.5. Okay. For continuous data, it's a little bit trickier. You have an infinite number of possible outcomes. Even if you have a starting point and an end point, it's still infinite, because you can, when you measure Tiger Woods Drive, it could be exactly, it depends on how fine you measure. You could always measure more and more precisely. You could say 300.000000925 meters. Like you can always go smaller and smaller, at least in theory, mathematically. I don't know if physically you can, but mathematically you can. So therefore, the probability of any one, that says one, outcome must be 0. And this is kind of like a paradox. I would say it's a paradox. So what really are you asking? So when we ask questions about probability, we must always determine probabilities for a range of outcomes, just like we did just now. With Tiger Woods here, we found the probability for a range between 330 and 340. We can't do exactly 330 because there is no area. We get a rectangle of 0 area. So we have to always do a range. All right, let's look at some other types. So we looked at uniform. Let's look at exponential. And the example of exponential is very similar to what we did last unit, waiting time. What was the waiting time example for discrete? It was what did we call it?
Was it geometric?
It was geometric. So this is very similar. This is the exponential distribution is the equivalent, the continuous equivalent of the geometric distribution that we did before in discrete. And just like its name, the probability of a specific event decreases exponentially. That's why it's called exponential. All right. So an example would be, again, we'll do probability density, and the probability of something happening decreases over time, and it looks something like that. It's just like the continuous version of what we did with geometric, and this would be the waiting time. For example, waiting time for a bus, or it could be in physics. There's an example of atoms that change. How do atoms change from one type of atom to another type of atom?
They decay.
They decay. What do we call that? I taught this last year, did you guys? Half-life. Yeah, it's
it is?
Yeah, it's half-life. It's radioactive decay, right? The nucleus kind of blows up. It breaks apart. So another example would be the time before radioactive decay occurs. That would be another example, but more in layman's terms.
Wait, sir.
Yeah.
Does it ever reach zero, or is that like an asymptote?
It never reaches zero.
No, it reaches zero. There is, in fact, that is the mode. The highest point of this graph, the mode is actually zero. But again, you can never determine the actual probability of. You have to do continuous data questions. We always have to do a range of probabilities. So between a range of times. So you can't do exactly zero, because exactly at zero it's zero. But you have to always do a range.
So like, does it ever hit the
yes, it does.
horizontal axis?
Yes. Yeah, it does.
Okay. How is that possible? If you take the half of anything and you keep taking the half again and again and again and again, you never get zero because there's always half of something.
It's just like the geometric series we had before. There's kind of like a paradox here, but
Okay.
it's hard to explain. Anyway, there is a mean value, like there's an average or mean, and let's say the mean. Guys, do you remember what letter we used for the mean? When you did that assignment for me, you remember that? I talked about.
Oh, it looked like a squiggly line.
Yeah, it looks like a squiggly. It kind of looks like a letter. Remember that? It looks like a U?
Yeah.
Okay. So this is the mean. There's actually two symbols for the mean, depending on if you're talking about a population or a sample. But if it's for a population, the mean is just this. It's the letter mu. Okay. It's a Greek letter mu. It's the mean. So there is an average waiting time, but there is a possibility that you get the result very quickly, or the result be very, very distant in the future. But there is an average. Okay. Let's look at what happens 99% of the time in real life situations is something called the normal distribution, and the rest of the unit is about the normal distribution. Okay, so normal distributions are found in many real-world instances, especially when sample sizes are large. In the normal distribution data, the data is clustered around. I'll show you what it looks like, and then you can fill in the blanks. The data looks something like this. I'm just going to call it PD, probability density, and it looks something like that. Is that exciting or what? All right. So, what do we call this? I'm saying this is the norm. What would you guys call it? Has a shape of a
bell curve.
Yeah. So this is bell shaped. It's bell shaped. And the most common occurrence. What do we call the most likely outcome of the one that's repeated the most? So this one looks like it's repeated the most. Whatever this outcome is, whatever we're measuring, this would be the
mean.
That's the median, isn't it?
No. There's three variables.
Mode.
Yeah, there's mode, median, and mean. And for this one, they're all the same, right? So the mode is the most common outcome. And whatever we're measuring, let's say this could be height in centimeters of population. So there would be a mode, which is the highest point of the curve. That would be the mode. So, but it so happens it's symmetrical, so that the mode is actually the same as the mean. So in this type of in normal distributions, the mean equals the mode equals the median. It is symmetrical. How do you spell symmetrical? Symmetrical. Oh, okay. Let's fill in. Oh, sorry. Let's fill in the blanks now. The data is clustered around the mean and the mode and the median, and is symmetric on either side. These graphs are also known as bell curves. All right. So if you measure a lot of things, IQ of population, height of a population, weight of a population, you typically get a bell curve, right? If you're making widgets in a factory, you can the length of whatever it is you're making, a screw or something like that, would probably have a distribution of a normal shape distribution. So it occurs a lot. Right? Last page. We're good? Yes? I guess so. All right. Sometimes you have modifications of the bell curve that look something like this. It's pulled. It's bell-shaped, but one side is pulled a little bit. So the mode would be right here. That's the highest point on the curve. But where would the mean be? If you have a lot of data,
It'll be close to where it's like curving down.
Yeah, the mean would be pulled this way, right? Does everyone see that? If you have these values here, kind of like almost outliers, the ones here pull the mean that way. Let's say the mean is here. Where would the median be? The point where half the population is below the median, half the population is above the median. Would it be over here somewhere, or would it be between the two?
Maybe between the two.
Yeah, you would be right. So, if these points that are high over here affect the mean the most, then the median, and they don't affect the mode at all, really. So an example would be, which one do you think? Skip the last one here. Out of these two, the number of children in a Canadian family, or marks on a very easy quiz, which one would be like this? So
marks on an easy quiz. That positively skewed.
So marks on an easy quiz, you would have like low marks here and high marks here. But if it's easy, where would most of the marks be? On the high side or the low side?
On the high side.
High side. So if it's an easy quiz. Let's look at the number of children in a Canadian family. If you look at kids, different families in your neighborhood, what do most families have in terms of number of kids? Two, maybe three, maybe one. You might have some families that have 10 kids, right? But that's pretty rare. So this one here, number of kids would be this one, right? This would be example with number of kids in family. Right? You would have a lot of people with 0, 1, and 2, and then very few with 9, 10, 11, 12, whatever, right? So this would be kind of more like what you would expect the number of kids in a family. And marks on a very easy quiz would be the other way. It would be something like, let's say that's 100%, and this would be like, I don't know, 0%. And so here you would have the mode again. Here you would have the median, and the mean would be over here somewhere. So for these ones here, for the number, so this is the marks on easy quiz. Marks on easy quiz, right? You would expect a lot of high marks and a few people that bombed it, but most people did well. And then number of kids in a family, most people have low number of kids, but few families have high number of kids. So with this type of distribution, the mean is greater than the median, which is greater than the mode. And it's the opposite situation here. The mean is less than the median, is less than the mode. Alright, so this is called positively skewed. Another way of calling this is it's skewed to the which direction? Oh.
Right.
Would you say right or left?
Right.
It's skewed right. The mean is skewed, like the mean is being, yeah, the tail is to the right. The mean is being skewed to the right. So we call this right or positive. It's skewed in the positive direction. Remember, this is the positive. That's the positive direction. That's the negative direction. So it's skewed positively. So it's positively skewed. So this is positive, and this is negative. Why is it negative? Because the tail is on the negative direction. The mean is skewed in the negative direction, and this tail is pulled to the left. All right. So what did we say? We said number of kids in a Canadian family is positively skewed. Marks on a very easy quiz is negatively skewed. This requires some explanation. Jay Leno was the guy before. I taught this course 12 years ago. Back then, it was a guy named Jay Leno. Now it's Jimmy Fallon. Everyone's heard of Jimmy Fallon? You know who Jimmy Fallon is?
Yeah.
Okay. Okay. And I don't know if he's like Jay Leno, but Jay Leno told lots and lots of jokes. But his jokes were not that funny. He told so many jokes. It was a few good jokes, but a lot of them were not that funny. So what was that? Would that be positively skewed or negatively skewed?
Positive.
Yeah. So why? Because lots of jokes, lots of. I don't watch Jimmy Fallon, but he might be totally different. But So you guys won't know who Jay Leno is. All right, and we're almost done. So a distribution with one hump is called unimodal. There's only one mode. What do you call something that has two humps?
A camel.
Awesome. Good answer. I like that. But in terms of probability distributions, something that has two humps is called bimodal. There's two modes. There's one here and let's say one there, right? All right. What would be an example? Give me an example. A population that is bimodal. Well, no guesses? When I was talking about population before, I kind of lied. Population is not, if I measured the height of everyone in Canada, of adults in Canada, let's say, people over 20 in Canada, I would probably get a bimodal distribution, not a bell-shaped, not a unimodal, but I would probably get a bimodal. Why would I get a bimodal instead of a unimodal if I measured the height of people in Canada? Tell me what the population in Canada looks like. There's two main groups of people in Canada that are kind of different in their heights. Can you name them? Ooh, I didn't expect this to be that hard. Roughly half the people are of one type, roughly half the people are of the other type.
Oh, like male and female?
There you go. Okay. So if you did, I don't know, could be height. It doesn't have to be height. Let's say shoe sizes. Shoe size of adult population. You would get a bimodal. Why? What would this mode represent?
Female.
Female. That's the female mode. What would this one represent?
Male.
Male mode. So, because women, generally speaking, have smaller feet than men. So, why bimodal? Men and women have different foot sizes, different size feet. And that's it. That's just an introduction to continuous probability distributions. There's a bit of homework. I posted some external videos. You should watch those. And that's it. I'm going to cut the video recording short and just stay there for a second. Stop it. That's not it. What am I looking for? How come I don't see it?